So let's talk about some practice problems and go through and see how some of the things are done. We did a little bit of, a run through of each type of these problems, one-way ANOVA, factorial ANOVA, one-way repeated ANOVA, correlation regression, and chi-square. Let's go through another example, sort of walk through different pieces so you can see how it's done and get a little practice doing these kinds of problems. So the first thing we're going to talk about is a one-way between groups ANOVA. These example problems, I think most of them are taken from the practice problems that are on Canvas, so you can see where the problems are coming from, what the setup looks like on paper, and we'll just walk through some of these. And for the one-way between groups ANOVA, I'll go through the deviation and the computational sort of approaches, so you can see the different options of sort of what to do. I'll even talk about the shortcuts and things. Okay, let's do it. So the first problem we'll talk about is sort of a silly one. I think one of my TA some years ago put together this practice problem, and it's a goofy one. It's comparing having people rate 3 different movies, comedies. If a couple of them, especially one, maybe is a stretch calling it a comedy, but the movie Old School, the original Airplane, and then the movie Corky Romano, which is a Chris Kattan movie that was not, I don't think it did very well, but which is why you sort of see the ratings differing there. But so researchers performed a study where people watched either one of these 3 movies and rated on a scale of 1 to 10 how funny they thought the movie was. And then the data follows over there on the right. So as part of the problem, you're asked to, if you're assuming these observations are independent, meaning that there are 15 different people that were assigned to the three different groups, 5 each. Run a one-way analysis of variance on this data. You're then asked to compute both eta and omega squared. You're asked to use individual comparisons, and specifically it says Tukey, to find where the differences lie between the 3 groups. And then you're asked this question at the end: why might it be troublesome to run an analysis of variance for these data? So we'll go through those one at a time. Obviously, the first one's going to take a little bit longer. Let's go through that. All right, so assuming these observations are independent, run a one-way analysis of variance for this data. All right, so one of the things I want to set up so that we keep it straight here is I'm going to make an ANOVA summary table. So I need to have the source. I need some squares. I need degrees of freedom. I need mean square. And then I need F. And the sources here are going to be the movie. All right, so movie is one source. That's the sort of between groups component. We're going to have within groups, in this case within movie. And we're going to have total. Let's just write it total. All right, so there's our source table. I'm going to put this in the box, make it look nice. So this is typically the goal. This is what you're trying to put together when you run an ANOVA, so that you can put together the pieces and come to an F and keep it nice and organized. All right, so we have our pieces, and we're going to put that together. There's our source table. All right, so let's go through them one at a time. Let's go through movie first. So we see here on the top we have our means. It doesn't give us a grand mean. Now for that makes it a little tricky. So no grand mean means that we're going to have to figure out what the grand mean might be. Now you could go through and sum up all the numbers and divide by 15, but because the groups are equal, we have 5 in each, we can just take the 3 means and average those out, and that'll give us a grand mean as well. So 6.2 plus 7.8 plus 4 gives me 18 as the sum. Okay, and I'm going to divide that by 3. This tells me that the grand mean here is 6. The grand mean equals 6. Okay, we're not given that number, but we can figure it out pretty easily. We're going to have to do a little extra work when it comes to, if we want to do those computational, the alternative sum of squares, because again, in this problem it's not given to us. So we may have to figure out a way to find that. But when we get there, we'll figure it out, I guess. So what's the equation we need for the sum of squares between groups? So for sum of squares between groups, we need, it's the sum of n for each group times the mean for each group minus the grand mean squared. So that's what we need for our sum of squares between groups. There's only 3 groups, so this is not too bad. Alright, so let's figure that out. We got, we know n is 5. Okay, so we're going to do 5 times each of those deviations squared, and we're going to add them up. So the first mean is 6.2. So the sum of squares between groups is going to equal 5 times 6.2 minus 6 squared. That's what's for our first group. Plus our second group, 7.8. So that's 5 times 7.8 minus 6 squared. Just one more. 5 times 4 minus 6 squared. And there's our 3 groups. So let's figure that out. So this is 0.2. 6.2 minus 6 is 0.2. So 0.2 squared is 0.04. So this part in here is 0.04 times 5. Maybe I'll use a different, let's do this. So 7.8 minus 6 is 1.8. Squared is 3.24, so that's just 3.24 in there. And then that's 2 squared, right? Yeah, negative 2 squared is 4 in here. All right, so I'm going to use a different color just to keep track of things. Use pink. So 5 times 0.04 equals 0.2. So this whole part in the brackets is 0.2. Okay, that includes 5 times the 0.04 is 0.2. 5 times 3.24 equals 16.2 here. And then 4 times 5 is 20. Okay, so we're going to add those up. 0.2 plus 16.2 plus 20 equals, this whole thing is 36.4. Okay, 36.4. Alright, so we can actually put that in here. 36.4. Alright. Now I realize I'm doing this a little bit out of order because it's just asking me to run one-way analysis variance. You should go through the 7 steps, and I'll show those in just a second, but I'm just sort of running through the sum of squares here first. So I'm going a little bit out of order. I jumped in right into the sum of squares. But so our first sum of squares is 36.4 for movie. Next, let's talk about the within groups. All right, so sum of squares within groups equals to the sum of, I need each individual score, right, so x, I, j, every score in every group, minus the group mean. Okay. So that means I'm going to take every score up here, every score, minus their own group. Alright, so sum of squares within groups equals. So it's 5 each, let's take, alright, so 7. I'll just lay these numbers out. 7, 6, 8, 8, 4, 6. Like that. And then the next 5 are 9, 10, 6, 7, 7. And then 3, 5, 2, 7, 3. 3, 5, 3, 5, 2, 7, 3. 3, 5, 2, 7, 3. So for the first group, because it is, they're all in this group here, I'm going to be subtracting out this mean, 6.2. So this minus 6.2 squared plus this 6 minus 6.2 squared plus this minus 6.2 squared. 4 minus 6.2 squared minus 6.2 squared. And we'll keep going to the next group. Alright, so the next one has a mean of 7.8. So minus 7.8 squared plus this 7.8 squared. This marker may be dying. And then the next group is 3, it's got a mean of 4. Minus 4. Minus 4. Minus 4. Minus 4. Minus 4. Okay. Let's change colors and sort of start adding this stuff up. Alright, so 7 minus 6, not plus, 7 minus 6.2 is 0.8, squared is 0.64, so the first one is 0.64. The next one, 6 minus 6.2 equals negative 0.2, squared is 0.04. Okay. So that means this one's also 0.04. And 8 minus 6.2. 8 minus 6.2 equals 1.8. Squared is 3.24. 4 minus 6.2 is 2.2. Squared is 4.84. And that's the first group. Let's keep going. 9 minus 7.8 equals 1.2 squared is 1.44. So this here is 1.44. Is there another one of those? Nope. 10 minus 7.8 equals 2.2 squared, 4.84. Alright. 6 minus 7.8 is a negative 1.8. Squared is 3.24. And then 7 minus 7.8 is 0.8. Squared is 0.64. 0.64. 0.64. 3 minus 4 is 1, squared is still 1, 5 minus 4 is 1, squared is still 1, 2 minus 4 is 2, squared is 4, 7 minus 4 is 3, squared is 9, 3 minus 4 is negative 1, squared is still 1. Right? 1 squared is 1, 1 squared is 1, 2 squared is 4, 3 squared is 9, and 1 squared is still 1. Alright, awesome. So let's add them up. Alright, let's go 0.64 plus 0.04 plus 3.24 plus 4.84 plus 0.04 plus 1.44 plus 4.84 plus 3.24 plus 0.64 plus 0.64 plus 1 plus 1 plus 4 plus 9 plus 1 equals, looks like 35.6. All right, one of the things we could do, just like, shortcut number one, potentially, is knowing that our between and within together make up total. I could skip computing the total altogether using the deviation form and just add these two up. So if I did that, I would take 36.4 plus 35.6 equals 72. So I could just go directly to calculating that as 72, and I can fill this out. And since I'm not using this for f anyway, I could do that and feel pretty confident I got those two. And I would do this only if I go through this carefully and I'm pretty certain that my between and within are correct, then I would go through and just add them up and get to total. Be pretty easy. Save you some time. But just in case, let's go through the total, the deviation form, and see if we get 72. Make sure that it all lines up. All right, for the sum of squares total, sum of squares total, well, when I do it through the deviation approach, is the sum of each individual and each group minus the grand mean squared. So this is another one where we need to do it for every single score. So every single score here needs to be included. The nice thing is I don't have to do it. I don't have to change the number I'm subtracting. It's going to be 6 each time. Okay, so this says total equals, so again, 7, 6, 8, 4, 6. 7, 6, 8, 4, 6, and 9, 10, 6, 7, 7, 9, 10, 6, 7, and 7. 3, 5, 2, 7, 3, 3, 5, 2, 7, and 3. And there's our values. Alright, and then all I'm going to do now is see 3, 5, 2, 7, 3, 5, 2, 7, yeah, as I'm going to subtract out the grand mean each time. Okay, so it means I'm going to take 7 minus 6 squared, 6 minus 6 squared, 8 minus 6 squared, 4 minus 6 squared, 6 minus 6 squared, 9 minus 6 squared, plus 10 minus 6 squared, plus 6 minus 6 squared, plus 7 minus 6 squared, plus 7 minus 6 squared. So it's supposed to be a plus. 3 minus 6 squared, plus 5 minus 6 squared, plus 2 minus 6 squared, plus 7 minus 6 squared, plus 3 minus 6 squared equals. Alright, so let's do all that. So my 6 is 1. 1 squared is still 1. 6 minus 6 is 0. 8 minus 6 is 2. 2 squared is 4. 4 minus 6 is negative 2. Negative 2 squared is 4. 6 minus 6 is 0. 9 minus 6 is 3. 3 squared is 9. 10 minus 6 is 4. 4 squared is 16. 6 minus 6 is still 0. 7 minus 6 is 1. 1 squared is 1. 7 minus 6 squared. 7 minus 6 is 1. 1 squared is 1. 3 minus 6 is negative 3. Squared is 9. 5 minus 6 is 1. 1 squared is 1. 2 minus 6 is 4. 4 squared is, or negative 4. Negative 4 squared is 16. 7 minus 6 is 1. 1 squared is still 1. 3 minus 6 is negative 3. Negative 3 squared is 9. All right. Let's add all those up. 1 plus 0 plus 4 plus 4 plus 0 plus 9 plus 16 plus 0. So plus 1 plus 1 plus 9 plus 1 plus 16 plus 1 plus 9 equals 72. So, yay! It all adds up. All right, so this does equal to that, which is good. All right, so that's all of the sum of squares. Again, there's nothing really difficult about this. I mean, the most difficult part is that we're squaring things. So your calculator does that for you, essentially. It's just keeping track of it. This is more of an organizational thing than anything else. Keeping track of all the parts and making sure you're adding things up right, not missing things, not adding up incorrectly, stuff like that. It's more organizational than it is complex, really. But let's keep going. So we have our sums of squares. So what else? We need our degrees of freedom. So let's talk about degrees of freedom now. All right, so there are 3 degrees of freedom. We need degrees of freedom for movie. We need degrees of freedom for within groups. And we need degrees of freedom for total. All right, so for movie, that's k minus 1, where remember k is the number of groups. But we can also think of this as we get into the factorial designs, we talk about a and b being levels. Since we only have one, it's essentially just a. So I can, instead of using k, I can think about the levels of our a IV as just a minus 1, whichever way you like. It doesn't make a difference. It's just the number of groups minus 1. So I have 3 groups minus 1 equals 2. For within groups, it's going to be the total number of subjects, which is capital N, minus the number of groups. So minus k, or if you like, again, n minus a, whichever way you like to think about the levels of groups. Either way, it is, I have 15 total subjects, total participants, minus 3 groups. So 15 minus 3 equals 12. For total, it's again the total number of subjects minus 1 degree of freedom. Now here, I lose 3 degrees of freedom because I'm talking about between groups, so I'm talking about 3 different means, 6.2, 7.8, and 4. So I'm losing 1 degree of freedom per group. For total, I'm subtracting out the grand mean. So I'm really only losing 1 degree of freedom because I'm talking about 1 mean. So this is going to be 15 minus 1 equals 14. All right, so we can write those in. So that means this is 2, this is 12, this is 14. And again, if you're calculating this, it's always good to make sure do these 2 add up to that one. So 2 plus 12 does equal 14. That's good. So far, so good. Now, once we get to this point, the rest of the table sort of fills itself out. We don't need to do a whole lot of other stuff here, because to compute, say, the mean square for movie, I'm going to divide it this way, right? 36.4 divided by 2, and then 35.6 divided by 12. So those are pretty easy to do. 36.4 divided by 2 equals, so this is 18.2. And then 35.6 divided by 12 gives me 2.967. 2.967. So now what do I do? Well, I want to get my f value. I simply divide it this way. Okay, I'll take 18.2 divided by 2.967. 18.2 divided by 2.967 equals 6.134. 6.134. Alright, so we got our ANOVA summary table, or our source table, filled out. That's great. Now what? Well, again, we sort of went a little out of order. I sort of jumped straight to, this is all part of, this would be all part of step 6 in our hypothesis testing stuff, right? This is everything we do in step 6. So let's go back a second and think about, let's cover those hypothesis testing steps to see what we can conclude about this 6.134. All right, so if we're doing the 7 steps, step 1, right, I can go back and forth on some marker colors. Step 1 is that is our null hypothesis. So in all of these, our null is simply going to be, I'm going to do a line step, that the mean of, say in this case, old school, I'll just say mean of old school equals the mean of airplane equals the mean of Corky Romano. Another way of saying this is that all means are equal. Okay, great. For step 2, the alternative then is, there's lots of different ways of saying this, that at least 2 means are equal or whatever. I just think of it as not all means are equal. Not equal, equal. Okay, perfectly fine. All right, cool. Step 3. What's alpha? Well, it doesn't say anything about alpha in the problem, so we're going to assume that alpha is, like it always is, 0.05. Okay. Step 4. Well, you were sort of told at the beginning, but if you see that there are 3 groups and it tells you that you can, something like, see, assume these observations are independent, and you have 15 people assigned to those 3 groups, it can't be a t-test, it's not a repeated measures because they're independent, so it's got to be a one-way between groups ANOVA. Okay. All these markers might be dying. Okay. Step 5. All right, we need degrees of freedom, critical value, all that stuff. So since we sort of started and did it a little backwards, because we started with step 6 here, we already had the degrees of freedom. So I know I need an F critical with 2 and 12 degrees of freedom. So that you have to look up. So let's do that. Let's find the critical value in our F table. Okay, so here's the F table for our alpha equals 0.05. And we said we had 2 and 12 degrees of freedom. So we're going to start off on this column for 2 there. And we're going to scroll down to 12. Right, so 2 and 12 degrees of freedom means we have a critical value of 3.885. Let me scroll up a little bit so you can maybe see it a little bigger. Okay, so we're going to start off with a 2. We're going to go down to 12 on this side and find out where those 2 meet. 3.885 is our critical value for 2 and 12 degrees of freedom and alpha equals 0.05. All right, as we saw on the table, this is 3.885. All right, so that means our decision rule is, all right, so if our f observed is greater than 3.885, we're going to reject. Okay, it's so hard to see. Reject the null. All right, pretty straightforward. So then what about step 6? Step 6 is what we sort of jumped into. It's what we did first, right? It's in the sort of table. Right, so it's in that source table there. This is really, we did everything in step 6 here already. We sort of started with that. So it's everything over in the table on the right. I already did it. So what about step 7? So we have an f observed. So we can say since our 6.134 is greater than 3.885, and we're going to reject. Okay. So since the f observed we found of 6.134 is greater than the 3.885, we're going to reject the null hypothesis. So what was our null hypothesis? That the means were equal. So we're rejecting that. So there's some evidence that people did not rate the movies the same, right? They did not think they were all equally as funny. Okay. So that takes us through the 7 steps. But let's go back for a second and talk about the alternative sums of squares, and maybe another shortcut we might be able to do in here as well. So let's talk about what if you wanted to do this through the sort of alternative sums of squares, right? So-called, keeping track of the sort of computational forms, even though it's all computation. Right, so it's computational sums of squares. What if I want to do that instead? All right, well, let's figure what those are. So here the sum of squares between groups equals, we got, for sum of squares between groups, it is the sum of aj squared over n minus t squared over a n. For within, it's the sum of y squared minus the sum of aj squared over n, and for total, the sum of y squared minus t squared over a n. Remember, t is the same thing as total, meaning the sum of all the points of all the. It's like sum y. And then this, we're squaring first and summing, so this is every value squared and added up. All right. So the issue is that in the example, you're not given those numbers. Now on an exam or something like that, you will be given these, so you have the option. But in this particular example, we don't have them. We don't actually have those numbers. So we got to figure them out. So So just so we're clear of where this stuff comes from. So if I want like the sum y, I'm going to take, well, like the sum y squared, I'm going to take every single number, square them, and add them up. And if I want the total, I need to add up everything. I also need the sums of each group, because that's what the sum AJ is. So I need lots of things. So let's sum up each group first. So 7 plus 6 plus 8 plus 4 plus 6 equals, so I have the sum for this one. So this sum up here, let's write it up here, is 31. Okay, 31 is our sum. So let's say these are the sums. These are the sums up here. Okay, so 31 for airplane is 9 plus 10 plus 6 plus 7 plus 7. All right, equals 39. Airplane, this is 39. Corky Romano, 3 plus 5 plus 2 plus 7 plus 3 equals 20. Let's do it one more time. I feel like I did something wrong. 3 plus 5 plus 2 plus 7 plus 3 equals. So for Corky Romano, the sum here is 20. And if I want the total, T, I can take 31 plus 39 plus 20 equals. So that means that T equals 90. Right, so our total is 90. So the last part, the last thing we need is the sum of y squared. So just one thing that's interesting too is you got this 6.2. So if another way to get the sums, 6.2 is our average. We know we have 5 subjects. 6.2 times 5 equals 31. 7.8 times 5 equals 39. And 4 times 5 equals 20. So you also can get the sums by using the means to, just take the means times the n, it'll give you the total. We used to go the other way around. We used to sum things up dividing by n to get the mean. Well, if we have the means, we have the n, we can actually multiply them to get the sums if we don't have them when we need them. Again, on an exam, this stuff would be given to you, so you don't have to do all this work. But when you're not on an exam, you have to sort of solve for some of this stuff. So to get the sum, so the other thing we need is the sum of y squared. Now that we have to take and square 7, 6, 8, 4, 6, and I got to square all these. Square 9, 10, I got to square each number, and I got to add them up. Okay, so I'm going to take in sum squared. So I'm going to take a shortcut. I'm actually going to use Excel just to do that real fast, so I don't have to watch me sort of sum and square things. Just in case you're interested, as an aside, if you want to, one easy way to get the sum of y squares is in Excel, there is a function. So if I go to pick up empty cell, it literally is sum SQ, which is returns the sum of squares of the argument. So it literally is going to square and sum everything up for you. All you gotta do is do that. Highlight everything here, whoop, and you get that the sum of y squared is 612. Right? So all I did was use a sum square function that will square and sum up all the values that you highlight. All right, so our sum of y squared is 612. So 612 is our sum of y squared. We just figured out with Excel. So again, these numbers will be given to you on exam. You won't have to do this, but just in case you want to know where they come from, how to get them, that's where you get them. All right, so the sum of AJ squared over n. So I need sum of AJ. So that's all these sums, 31, 39, 20. 31 squared plus 39 squared plus 20 squared over n is 5. Alright, and you subtract from that our total squared, 90 squared over our a times n, which is another way of saying big N. So 3 levels of a times 5, so that's 3 times 5 is 15. Okay. So let's figure out what those values are. 31 squared plus 39 squared plus 20 squared equals 2008.82 divided by 5, which gives you 576.4. So this here is 576.4. Okay, 576.4. 90 squared divided by 15 equals 540. So if I subtract those two, 576.4 minus 540 equals 36.4. All right, awesome. So going back to here, I have some y squared already given to me, 612. And I know the sum of aj squared here, because I just figured it out, is this 576.4 number. So if I subtract those two, 612 minus 576.4 equals, those are 35.6. All right, 35.6. So far everything's matching up. For total, I have all these pieces as well. So this is again 612. T squared over an is this 90 squared over 15, so I already have that too. 540 equals 612 minus 540 equals 72. 72. Alright, so we can find the same values for the sums of squares using this alternative form. Right, that's actually not too bad, not too hard. All right, so we can still get the same numbers here. Once we have those sums of squares and the degrees of freedom, finding the mean square is the same, finding f is the same. So let's talk about, just before we move on to the next part of this, let's talk about one other additional time saver. I often refer to this as a shortcut, but I'm thinking maybe shortcut sounds bad, right? Shortcuts are not, you're not supposed to take shortcuts. But additional time saver that you can use with this is because you're given the standard deviations, this 1.483, 1.643, and 2, because we're given those, we can use that to our advantage a little bit. So let's remember this idea of a pooled variance, where we can sort of average variance out. Well, if the groups are all equal, which they are here, we can simply just take the variances of the three groups. All right, I can add them up. I can divide by 3. Well, that's the same thing essentially what we're trying to do with the sum of squares or the mean squares within groups. So this actually really is the same thing as the mean square within groups. So the only trick is I'm given standard deviation, so I have to square them to get variance. So that means I can take my 1.483 number here, so 3, I can square that. I can add to that my 1.643, square that, and add to that my 2, 2 squared, and I can divide those by 3, and that'll give me my mean square within groups. All right, so let's check it out. 1.483 squared plus 1.643 squared plus 2 squared equals 8.89738, or something like that. Divide that by 3, and I get 2.966. 2.966, which is remarkably close to this. I mean, it's the same. Again, it's just a rounding issue, but so I'm able to jump directly to the mean square. And if I have the mean square, if I go directly to that, it saves me all those sort of subtracting and squaring from doing the deviation approach or something. I can actually go directly to the mean square, and if I know I have 12 degrees of freedom, I can simply multiply across let's say I got 2.966 is what I got from this, right? Times 12 equals, I get 35.592, which I would round up to 35.6 essentially, and I could fill out the rest of the table. And if I did the between groups and I did the within groups this way, I can then add up and get the total without having to do any of the long deviation approaches that we did as part of this example. It would take you a lot less time. Again, that's possible because all the deviations and stuff have been done for you and giving you these standard deviation estimates or calculations as part of the problem, right? So that's another way of saving time. We can actually go directly to this mean square, compute the mean square value directly, and then use that to fill out the rest of the table if necessary. So let's go on to talking about the other parts of this. So after the F test, it does ask you to calculate eta and omega squared. Okay, so let's talk about those. So eta is the one that's really straightforward. So eta squared equals the sum of squares between groups over sum of squares total. That one's pretty easy. Our between groups here is the one for movie. So it's simply going to be, or even change color. This is going to be 36.4 divided by 72, which equals 2. 36.4 divided by 72 equals 0.506, which, again, is roughly something like 51% if you sort of round it up. So eta squared says there's roughly 51% of the total variability is due to differences between the movies. So people's ratings of the different movies actually is driving more than half of the variability between individual scores. Okay. What about omega squared? Omega squared is, start off with sum of squares between groups. And you subtract out k minus 1 times the mean square within groups. Okay. You divide that by the sum of squares total plus one of those mean square within groups. Okay, not too bad. It's more complicated than eta squared, but still not too bad. It's still not like crazy complicated. So for this sum of squares between groups is the same number, 36.4. I'm going to subtract out, well, I know my k minus 1 is 2, so I'm going to take 2 times that 2.967, divide that by, these markers I think are dying, I'm going to divide that by the total, 72, plus one of those 2.967s. Let's figure that out. All right, so 2 times 2.967 equals 5.934. All right, so let's do that here. So this part here is 5.934. Right. So I'm going to take and my 36.4 minus 5.934 equals, okay, so that means down here, let's do it this way, yeah, this is going to be on top, I'm going to have 30.466 on top, and then on the bottom, I'm going to have 72 plus 2.967. 0.967 equals, this down here is 74.967. So when I divide those, 30.466 divided by 74.967 equals 0.406, which means it's rough. This one's saying it's roughly 41%, not 51%. Okay, so there's quite a difference there between the eta and omega squared values. But you interpret them the same. Okay, so this is saying that there's 51%. That's just saying it's 41%. What's the difference? Why would we do one versus the other? Just as a reminder, eta squared is more of a sample statistic. Remember I mentioned this, the one place where we sort of go against the norm and we actually are calling a sample statistic a Greek letter, which makes it seem like it's a population value, but it isn't. And technically, the omega is we're using sample values, so it's a better population estimate. Usually you'll see it as omega hat squared. So this is supposed to be more accurate. This one's is more of a descriptive statistic about your sample, and it's oftentimes overestimated, meaning that if you were to compare this to what it really is in the population, this would be too big. So omega squared is a way of trying to adjust this so that there's a better population estimate, which is oftentimes why you see it with that little hat on there, this estimating the population value. So this is supposed to be a more accurate representation of the population. This one's more of a sample statistic describing the data that you have, but it overestimates when it comes to inferring to the population. So the last couple parts here, the first is let's use individual comparisons, specifically Tukey, to find the true differences. Okay, so a Tukey test requires computing something called the critical difference. Okay, the critical difference for Tukey, and Tukey, so by the way, it's called Tukey's honestly significant difference test. Right, the Tukey's honestly significant difference. There's a few different ways of computing the Tukey's honestly significant difference. The easiest is to find what's called the critical difference, which equals, we're going to find some value q, and we're going to take and divide, we're going to multiply that by the mean square for within groups over Rn. Again, this assumes that n's are equal. In this case, they are. I think in the notes it says n sub a, but we're assuming that n is the same number across. So we need to find those numbers. So we know what the ms within groups are. We know what n are, but we need to find q. And Q is a value in a table. So we need to go to the Q table, which is either labeled the Q table or it's called a studentized range statistic. All right, so I had mentioned a while ago about, this is some time ago in the lecture, about I think his name was Louis Gossett or something like that, had published a paper under the name Student, where he looked at he was looking at how to sample beer working for Guinness, and they figured out a way to sort of correct for things, and he published this idea of an adjusted value under the name Student. So you'll see a lot of things related to that, sort of referred to by students. That's why you see the studentized range statistic. It's this idea of studentized, which comes from this adjusted, these adjusted t values that he put together when sampling beer from populations of beer, or grains from populations of grain working with beer in the Guinness factory. So let's look up the value for Q. So here's the studentized range statistic. Okay, and I know there's some writing in the way, but you see the table, and it asks for two things. On the top, instead of asking for the degrees of freedom between groups, which is what a lot of these tables ask for, it's asking for the total number of groups. All right, so we have 3 total groups, and then we need the degrees of freedom for within groups. So the degrees of freedom within groups we had figured out before. If we look quickly back here, we figured out was 12. So we have 3 groups, 12 degrees of freedom for error, or for within groups. So we can now go down to here, 3 and 12, and it gives us 2 options, either for alpha 0.05 or alpha 0.01. Since it says nothing about the alpha level, we can assume that it's 0.05. So with 3 groups, 0.05 alpha, our Q value is 3.77. Okay, our Q value is 3.77. So let's put these together. We got from the table that this is 3.77. This, we know the mean score within groups is at 2.967 number, 0.967, and our n is 5, so we should be able to compute all that. All right, so 2.967 here divided by 5 equals 0.5934. If I take the square root of that, it's 0.770 essentially. So this ends up being 3.77 times 0.770, which means our critical difference value here, critical difference equals 3.77 times 0.77 equals 2.903. 2.903 is the critical difference. So what does this do for us? So this tells us the minimum difference between group means, that critical difference, for groups to be significantly different. So we can compare those means by, okay, let's look at, and we can take old school versus airplane. Right, so old school versus airplane. We have a mean of 6.2. Let's actually do it in the, in an order that makes sense. So it's going to be 7.8 for airplane. Old school is 6.2. So if I subtract those two, 7.8 minus 6.2, 7.8 minus 6.2. You might be asking, why am I not doing the other way around? Because we really want the critical difference. So even if I subtract the 6.2 minus 7.8 and I got that difference as a negative number, I'm really interested in the absolute value. So because I want to know if the absolute difference between those is bigger than this number. So 7.8 minus 6.2 equals 1.6. All right, 1.6 is smaller than 2.903, so these are not different, or not significantly different under a two-key adjustment. All right, what about airplane and Corky Romano? So let's look at airplane. Versus Corky Romano. There we have 7.8 and 4. If I subtract those, 7.8 is going to be 3.8. Since that is bigger than 2.903, they are different. There's a critical, it's bigger than a critical difference. So under a two-key test, these are significantly different. And the last comparison would be looking at old school versus Corky Romano. It's going to be the 6.2 and 6.2 versus the 4 equals 2.2. Okay. And since 2.2 is less than 2.903, this is not significantly different. So the basic idea is, what we can conclude with this is, yes, there's a significant ANOVA. We know there's differences someplace, but given a two-key honestly significant difference test using the critical difference here, we can only really conclude that people rated airplane significantly funnier than Corky Romano. But all the other comparisons are sort of non-conclusive. We're not getting a significant difference with those, so we can't conclude anything else. So the main difference that seems to be driving the ANOVA here is that airplane was rated as significantly funnier than Corky Romano. The last part, I don't really need to write anything down for, but why might it be troublesome to run analysis of variance for these data? So you need to think about the assumptions. So we assume lots of things: normality, homogeneity of variance, independence. Independence, homogeneity of variance doesn't seem to be a problem. We didn't directly test it, but these variances are not too different, so I'm not too worried about that. But we have 15 total subjects. So I have only 12 degrees of freedom for within groups, so it's a rather small sample. So one of the ways in which we're able to assume normality of a sampling distribution is we either are told that the population is normally distributed. Right? That's one way. We were just told that. The population is normally distributed. So here we're talking about ratings of comedy, right? How funny something is. I don't know if that's normally distributed. It might be, might not be. I don't really know. And there's no statement in the problem about it being normally distributed, so then we have to rely on having a large enough sample. So typically with ANOVAs, the way we sort of meet the central limit theorem version of normality is to either have a normal population or to have enough people. So what's enough? Well, at a minimum, you usually want to have at least 20 degrees of freedom for your within groups. So that 20 seems to be a magic number. We talked about t-tests, like with a one-way, we need to have 20 people. We need to have 20 people in each group for independent samples t-tests. So we need to have, so we always had these sort of, 20 is the minimum number. And the same thing goes here, that we want to have at least 20 degrees of freedom here. Some places you might read you need to have 20 people per group, which is quite a lot. It means you'd have to have 60 participants. But at a minimum, you should have at least 20 degrees of freedom for your within groups, and we don't. So it's problematic here because we don't know if we can really trust the analysis. We don't know if it's really going to distribute normally. We don't know if the means would distribute normally given the central limit theorem, because we don't know anything about the population and we don't have enough people. So this is where doing this test may be problematic, because this may not be this may be biased in some way. We don't know if this really is a true reflection of the differences. So that's why it's problematic. Doesn't mean you can't do it. It just means that if you were to do this, you need to be careful interpreting or putting too much weight behind the F value and the significance of this test.